In 1935, Einstein, Podolsky, and Rosen sat at the traditional 3 o'clock tea at the IAS, and they came up with their EPR quantum entanglement paradox, the famous paradox. Fast forward to September 2021, and an only slightly less earth-shatteringly important event occurred, which was when Shang-Chi, who we've just heard from, and I were sat at tea, and he mentioned to me this plot, which is essentially another version of the same thing you've just seen. He's telling me here, as you can, I'm sure you can tell what he's saying, but he's telling me about this superthermal eccentricity distribution for the widest binaries. And in particular, he's saying that for 10 to the 3 AU and 10 to the 4 AU separations and larger, dynamical effects become important. So scattering from passing stars and molecular clouds and so on, and also the effect of the galactic tide. Okay, this is the plot he's telling me about. This is the superthermal distribution, and here is the thermal distribution, where the probability of having a particular eccentricity is proportional to eccentricity. And we have an excess of very, very highly superthermal, highly eccentric binaries at the wide separation end. So he's telling me that, you know, the galactic tides could be important here, and I jump on the chance and say, well, my entire PhD thesis was about wide binaries in external potentials. So I think there are 3 things that can affect wide binaries. One is formation, one is encounters with passing stars, and one is galactic tides. And I don't think we understand any of these 3. I'm going to completely ignore the formation. I'm actually going to be agnostic about how the eccentricity distribution forms originally. And I'm not going to think anything about, I'm not going to say anything about encounters. I'm just going to focus on the galactic tides. So what effect does the galactic tide have on wide binaries? We already heard it earlier when we were talking about comets. So Heitzer and Tremaine found in 1986 that if you take a comet moving around the sun and it's perturbed by the galaxy, you effectively have a 3-body problem. And the galaxy is able to pull that comet orbit to very, very high eccentricity. And the sun-comet system is just another kind of binary. That's basically because this is just a hierarchical triple. Okay, so your basic hierarchical triple theory tells you that if I have a red and blue binary here with semimajor axis A and eccentricity E, and a green star is going to perturb the red and blue binary, I can write the Hamiltonian for this system, for the inner binary, the 2-body system, as H0 of A, which is the Keplerian part, plus H1, which is the perturbation due to the 3rd body. I can then tidally expand the equations of motion of that red and blue binary, and I can average the motion over the inner Keplerian orbit and the outer orbit of the green star as it moves around. And on timescales longer than either of those 2, I get 3 conserved quantities. One is a semimajor axis, and one is this angular momentum, this cosine constant, square root of 1 minus e squared cosine I. And the third one, this is Lidov-Kozai dynamics. This is the Lidov-Kozai Hamiltonian, 2 plus 3 e squared minus 3 cos squared I minus 15 e squared sine squared I cos 2 omega. Can you tell I've given this talk before? Now, all 3 of these are conserved. What does that mean? That means that I can plot the binary evolution in a plane like this. So this is eccentricity on the y-axis, and omega, which is the argument of pericenter, just tells you how the binary is oriented on the x-axis. And these black curves are curves of constant Hamiltonian, the thing at the bottom, which means that every binary, you can put it somewhere on this plot, and it will be stuck to one of these black curves, okay? So maybe you start off at eccentricity of 0.2, and you move up to very, very high eccentricity, and then on long time scales, you move back down, and you undergo these Kozai oscillations. But there's absolutely nothing special about a point mass. That green star needn't be a point mass. I can replace the green star with the entire galactic disk and get something very, very analogous. Here, the Hamiltonian is 2 plus 3 e squared sine squared I minus 5 e squared sine squared I cos 2 omega. In fact, to me, these are both special cases of the most general thing you can do, which is to put any binary in any axisymmetric potential, derive a Hamiltonian that looks like this, where this capital gamma parameter tells you everything you need to know about the potential in which the binary sits and its orbit around that potential. So to me, the Kozai is just the special case where gamma equals 1, and the Heisler-Tremaine problem is the special case where gamma equals 1/3. Okay, so that means that we know very, very well how to solve for the dynamics of a binary in time for one binary, but we don't observe the time evolution of one binary. The period is 1,000,000 years. What we see is a snapshot of the distribution function of all the binaries today. How do I work out what that's going to be? The way I do it is like this. So I define J, which is the dimensionless measure of the angular momentum, to be 1 minus e squared, square root. And I plot that here on the y-axis. On the x-axis, I again have this omega angle, this argument of pericenter, and then I have my cosine constant, Jz, on the, well, z-axis or whatever that is. And now I'm plotting the distribution function f, these colors, which means that there are lots and lots of binaries in the red places and not many binaries in the blue places. Now, what's going to happen, any binary, remember, sticks to its black contours. It sticks to its Hamiltonian contours. So at a constant Jz, a binary is going to just move around the phase space like this. And that's where you see what's painted on the very front. What that means for a distribution function is that we're back to session 1, we have phase mixing. Okay, so the distribution function f is going to phase mix according to df by dt plus f comma h, which is a Poisson bracket, equals 0. This is a collisionless system, and all I'm doing is taking individual binaries and evolving them around their individual contours, and this is how the distribution function changes. So this is what the galactic tide is going to do to binaries on very long timescales. In other words, if I select a particular slice, so here I've sliced the this wedge at the top, I've sliced it at Jz equals 0.1. Initially, it looks like this. On the left-hand side, you see that the initial density distribution, the phase space distribution, doesn't depend on this angle omega. And after very long timescales, it has become phase mixed, which means that the density has been smeared evenly over these Hamiltonian contours. Okay, so this is what phase mixing looks like in the time asymptotic limit. And I can calculate this analytically in quadratures, and then I have to do one numerical integral to get what this final distribution is in the three-dimensional phase space. Then all I have to do is integrate out the stuff I don't care about to get the resulting eccentricity distribution, okay? And that's going to be the phase mix distribution that the galaxy is going to induce upon the wide binaries. You might ask, what's this timescale for this? So the typical secular timescale is about 10 to the 9 years for a binary of 10 to the 4 AU. Remember, that's the kind of range we're looking at. The timescale for this phase mixing is a few secular timescales. So really, we're talking on the billions of year timescale. So really, it's only these very wide 10 to the 4-ish binaries for which this approximation is going to work. And what happens? Only look at the left column. I'm completely agnostic about what the initial distribution of binary eccentricities is. I have no idea. So I'm plotting the initial distribution in red and the final distribution in black, and I'm comparing it to the thermal distribution, which is the dotted curves. What you see is that if I start off with a uniform distribution, that's the red one in panel A in the top left corner, I add a few binaries at high eccentricity, I take away a few binaries at low eccentricity, but it's still nowhere near thermal. It's still nowhere near solving the problem that Changshi set us earlier, is where do these superthermal binaries come from? Similarly, if I take an initially subthermal distribution, I end up with a subthermal distribution. I still can't solve the problem. It turns out that if I put in a superthermal distribution, which is panels C and D, I again get out a superthermal distribution, but that kind of kicks the can down the road because you've got to produce one to begin with. So that's almost my conclusion. The other thing to say is that the galactic disk actually produces a special direction in this problem. So your final distribution is not even isotropic. Okay, so you start off with a distribution of binaries that's isotropic, and the final phase mix distribution is not isotropic, and I can predict what the distribution ought to look like. I won't go into it now. I'll skip to the conclusion. The two-line conclusion is galactic tides can maintain but cannot produce a superthermal eccentricity distribution, so I don't know how to solve the problem, I'm afraid. And the second thing is that unless the initial distribution is both thermal and isotropic, the final distribution will be neither thermal nor isotropic. That might help us in how we look for understanding binary formation in the future. I still don't know what scattering does. I still don't know if that can make the distribution function superthermal. And if that doesn't work, we're basically back to formation. And like Shang-Chi said, especially for these twin wide binaries, we've got no idea how to make them so eccentric. I'll stop there. Thank you.
Hi, Chris. Very nice talk. And Xiangwen. You said scattering, but there's also the bar, spiral arms crossing the galactic disk, which presumably you could put in pretty easily.
Yes, that will be part of the scattering calculation. As far as this, I'm taking into account the global component of the global component of the potential. The spiral arms tend not to matter for that because the tidal forces depend so strongly on your local density. Unless you're in resonance with a bar or with a spiral, they kind of pass through, give you a perturbation in one direction, then pass through and give you a perturbation in the other direction. It washes out to nothing. But it's certainly true that if a spiral arm passes through a binary, that means lots of extra perturbers, and we don't know what's going to happen there.
Might be interesting if you gave a calculation of what you expect when you are in resonance, and we look at those orbits.
I can do that.
Great, and that ends this session. Thanks again to Chris.